welcome back to Manish Kumar channel. So today we are going to discuss about the properties of complex number with some examples. So if we list the properties before going to define, let us see that you have a complex number, and you know complex number is of the form x plus iy, where x and y belongs to R, and I square is equal to -1. We have already discussed in the first video, this is not an ordered field, complex number C, right? And because of the property that I square is not equal to positive quantity, I square is going to be negative. How do we define addition? Let Z1 and Z2 be two complex number of the form Z1 plus Z2, then their sum will be component wise addition. If you see component wise addition, x1 plus x2, and then component wise addition, y1 plus y2 I. Multiplication, if you want to do multiplication, is just the usual multiplication. So we will here separate real part and imaginary part together, right? Then modulus of z is nothing but square root of x square plus y square. Now if you see my first video, you will find that this is not an ordered field, not ordered field, right? So how do we define order? When we say that any complex number x1 plus iy1 and x2 plus iy2, which one is bigger, which one is smaller, is very difficult to say because of the fact that I square is going to be -1. So now the modulus concept comes into the picture. If you have two numbers in complex plane z1 z2, then you can say that modulus of z1 and modulus of z2, and assume modulus of z2 is greater than z1 or less than or equal to z1 or equal to, it depends upon the square root of the x component and y component, right? So now the idea of we can order them using the modulus concept, right? Suppose if you have 1 plus I and 1 plus 3i, right? So if you take the square root, 1 square plus 1 square is going to be root 2, right? And for this, if you calculate modulus, modulus of this number and modulus of this number is going to be 1 plus 9. So this is going to be root 10. So of course root 10 and root 2. So root 2 is less than root 10. So in that way you can order. So ordering is defined as this is not an ordered field. So we are defining order using the modulus property, right? Modulus of any complex number we have to take, and then we can compare which modulus is bigger, and in that way we can say that this complex number is bigger than the other complex number. Only the sense of modulus only, right? Otherwise we cannot say directly z1 and z2 are two complex numbers, so you cannot define order. Okay. Similarly, the division z1 by z2, provided z2 should not be 0. It should not come as an indeterminate form, right? Also conjugate. How do we define conjugate? If z is x plus iy, then conjugate is denoted by bar, right? Z bar. Z bar means if you have a complex plane, uh, then you can say this is I and this is x-axis, this is y-axis. So any point x comma y can be written as x plus iy type z. Assume z is here. If you take z bar means this point will come as the actual distance, you can say, right? Z bar. Z bar means this point, right? So this point is z and this point is z bar, right? So it means that the x-axis will play a role of mirror, right? Assume this x-axis is a mirror, then conjugate will be the mirror image of your z. So z bar, so x-axis will play a role of mirror here, right, for conjugate. Okay, so now conjugate means if you see here, x-axis is playing a role of mirror means your element becomes x minus iota y. It means that you have to change the sign of imaginary component only while taking the conjugate, right? So let us see how to represent in argand plane. So in argand plane, we declare y-axis as imaginary, which is denoted by im, and x-axis as real, right? And you can say any point from origin. This red one is z1 equal to x1 plus iy1, and blue line denotes the z2, another complex number. So it means that you have to run x-axis with x1 distance and y-axis height will be with y1, right? Then you can write that x1 plus y1, iy1 is this complex number. Similarly, if you want to run x2 axis and then y2 height, then this is going to be your y2 height, so y2, so x2 plus iy2. Like that you can represent in an argand plane, right? Assume how we have calculated the modulus, square root of x plus x square plus y square. So 2 square plus 1 square, and that is nothing but 4 plus 1, 5. So this is the modulus value of any complex number, right? So now let us see one example on these properties. So addition, suppose z1, z2 with two number is given to you. So how do you add them? So addition means component wise addition, right? Component wise addition. So 1 plus 2, 3, and 1 plus 1, 2. So the final number is 3 plus 2i. Similarly, multiplication. Multiplication, you know how to do the multiplication, right? Using the given formula above. Just simple multiplication and then try to take component of I in one side, means we are going to represent real plus imaginary part, right? So real part and this is imaginary part. Okay, and we have already seen how to calculate modulus. So modulus is also going to be root 5, right? And conjugate means if z is 3 plus 4i, then conjugate means z bar, and change the sign of I component. Whatever the I is there, then you can say that minus I. Suppose z is 3 minus 7i. So what is z bar? Z bar is going to change the sign of I. So 3 plus 7i. This is how the conjugate works, right? And division of complex number. So let us take two numbers z1 and z2. I am going to divide z1 by z2 provided z2 is non-zero. Then what we have to do is multiply the numerator and denominator by the conjugate of z2, right? So conjugate of z2, conjugate of if I say z1 is this divided by z2, so conjugate of z2 is 2 minus I. So conjugate of z2 is 2 plus I, right? So what you have to do, you have to multiply the numerator and denominator both by the conjugate of z2, right? So conjugate we are going to multiply, and then you know how to do the multiplication. Use the multiplication to get the resultant value. You can also simplify 1 by 5 plus 3 by 5 I. You can also write real part of z1 by z2 is the 1 by 5, and imaginary part of z1 by z2 is 3 by 5. So you have to separate it out these values, 3 by 5 and you have to separate out the real part, right? And we have some properties and modulus of z. So any complex number z1 and z2, then real part of z modulus is always less than or equal to mod of z. Imaginary of z is always less than or equal to mod of z. Equality holds real part of z is modulus is equal to mod of z. Equality hold if and only if your z is real only. Z is real only means z can be any real number. Z can be of the form of x only, right? And plus you want to write into the complex form, so 0 into I. Imaginary part must be 0 in that case. So whenever you take real part of z, which is going to be x, and if you take modulus of z, which is equal to square root of x square plus 0 square, which is nothing but square root of x square, and that is nothing but x, right? And in that case, uh, your your x must be positive in that case, right? Because you are going to take a square. So in that case, you say modulus of this value, modulus of this value is equal to the modulus of this value, right? You got my point or not? So modulus means positive value. Okay. So x greater than 0. So modulus of x you can write. And in that case, modulus of z is equal to modulus of real part of z. Similarly, this will be equality will be hold if uh, z is only imaginary part. Z equal to imaginary part, right? Means real part is 0. And another property, root 2 times of mod z is greater than or equal to real part of z plus imaginary part of z. Minus of mod of z is equal to mod of z. Mod of z1 plus z2 is less than or equal to mod of z1 plus mod of z2. This is triangular property that is true in your real number case as well. Okay. And fifth property is very, very important. Z1 minus Z2 is greater than or equal to mod of whole mod of mod Z1 minus mod Z2. Proving fifth inequality is easier because you can say that mod Z1 can be written as mod Z1 minus Z2 plus Z2. I'm going to add something and subtract something, and using the triangular inequality. Triangular inequality will be mod Z1 minus Z2 plus mod Z2. So I'm sending this factor other side. So what can I write? Mod Z1 minus mod Z2, right, is less than or equal to mod Z1 minus mod Z2, right? Similarly, I'm writing mod Z2 minus mod Z1 is less than or equal to mod Z2 minus mod Z1. And mod Z2 minus mod Z1 is nothing but mod Z1 minus mod Z2, right? Because negative I take common and then modulus of negative is positive. So now if I want to write this factor here, negative side minus, I can also write mod Z1 minus mod Z2, right? Is less than or equal to mod Z1 minus mod Z2, right? If you look at these two inequalities, right? So what you can conclude that the same quantity here, and this is the same quantity with negative side. So it reveals that mod z1 minus z2 is greater than or equal to modulus of mod of z1 minus mod of z2, right? So this is a very simple proof you can do so. Okay. So now, so conjugate properties, modulus of z bar is equal to mod of z. Z bar is equal to mod z square. Z1 plus Z2 whole bar is equal to mod Z1 plus mod Z2. Z1 minus Z2 whole bar is equal to mod Z1 bar minus mod Z2 bar, right? Z1 Z2 product bar is equal to product of their individual bars. Z1 by Z2 whole bar is equal to Z1 bar by Z2 bar, provided Z2 not equal to 0, right? Similarly, real part of Z is equal to Z plus Z bar by 2. You can very easily find out this property. You see, Z equal to X plus IY, Z bar is equal to X minus IY. So if I add these two equations, so this is going to be uh, cancelled out. So here Z plus Z bar is equal to 2X, and which is nothing but X is equal to Z plus Z bar by 2. This implies real of Z. X is the real part of Z, right? Z plus Z bar divided by 2. So you can easily derive the other part as well. Z minus Z bar divided by 2i. If Z is real, if and only if Z equal to Z bar. So if Z is only real, then G bar is equal to G. Let us do some exercise. Sketch the set of points determined by the condition, right? So we have to find the set of points. Z is X plus IY. So what about Z bar? X minus IY, right? So real part of Z bar minus iota is equal to 3, and real part of Z means X minus IY and minus I equal to 3. Again, real part of X, and you can take common Y plus 1 times of I is going to be 3. So this is X plus IY type. So real part is going to be X only. So X equal to 3. So it means if you have a plane and then the points are X equal to 3. So this means all the points sitting on this line, right? So this is the solution set. Okay. So point will be a line parallel to y-axis, and this is going to be x equal to 3. All those points on x equal to 3. So next part, uh, modulus of 2z plus I equal to 4. So you can easily solve this one. So if you take first we have to calculate z means 2x plus iy and plus iota is equal to 4. So first let us simplify. So 2x and 2y plus 1 into iota is equal to 4. And you know modulus property, square root of 4x square plus 2y plus 1 whole square, right, is equal to 4, right? If I square both sides, what am I going to get? 4x square. And then now I'm taking 2 common from here. So 4y plus half whole square, right? And squaring both sides will give you 16, right? So 4 will cancel out this by 4. So what am I going to get? X square plus y minus half. I'm going to write this one, and whole square is equal to 2 square. So this is nothing but a equation of circle where center will be 0 and minus half and radius will be 2, right? Similarly, show that real part of z plus z bar whole square modulus is less than or equal to 4 when mod z less than or equal to 1. So you can solve this. The solution is already provided in the next slide. Similarly, factorizing z power 4 minus 4z square plus 3 into two quadratic factors, and show that if z lies on the circle z equal to modulus z equal to 2, then this holds. Okay, so now this is the solution. Okay, solution to 1. So similarly, you can just expand it using the properties. You can find this, and similarly you can do problem third as well. Okay, so thank you very much. Thanks a lot.